All right, everybody, welcome to chapter 10. We're talking about probability in this chapter. It's going to be a great chapter. So, in this lesson, we're going to review ideas of probability. So, we'll use some of our ideas you've learned before, things such as systematic lists. We're going to learn about tree diagrams and area models. And then you're going to use your tools to. Certain tools may work better in other particular problems. So, we'll talk about which ones to use when. And then we'll talk about in one problem, a tree diagram or list might be most efficient, and then also talk about area models and when they will be best. And we're also going to talk about expected values and whether games are fair or not. So we're going to start off with a problem that involves rock, paper, scissors. So you may have seen that. It's going to be a variation of rock, paper, scissors, though, because you're going to have three people playing at a time. So we're going to say that there's a person A, a person B, and a person C. And person A, that all three would be playing at the same time. And person A gets a point if all three match at the same time. So, like, for example, rock, rock, rock. Person B would get a point if two of the three players match. So if it was like two rocks and a paper. And then person C would match if none of the players match. So a rock, paper, and scissors. So obviously, if I have done this before, and this is just some of the data that I've gotten one time before. In this case, we had that person A won 3 times, person B won 13 times, and person C won 4 times. So after looking at this data and our experimental results, does the game is fair? Does the game seem fair? And by definition, a game is fair if over many plays a person would expect to neither win nor lose points or money by playing the game. So in this case, this game clearly should not be fair because B won a large amount more wins than A and C. A and C are fairly close, but B won a whole lot more. So we're going to say no. Player B won a lot more. And so now what we're going to do is we're going to calculate the theoretical probability. So this was kind of like our experimental probability, 3 out of 20, 13 out of 20 because we played 20 times, and 4 out of 20. But now we're going to calculate the theoretical probability, which is what should have happened. So theoretical probability describes how likely an event will occur, and we're going to use this formula. And you probably have seen this before. Probability, so we always write probability with this capital P, and then whatever we're trying to find the probability of is going to go inside parentheses and is equal to the favorable outcomes over our total outcomes. And to calculate this probability, we're going to calculate or create something called a tree diagram to see all the possible outcomes in the sample space. So the sample space, if you look down here, sample space is the set of all possible outcomes of an experiment. And a tree diagram can be used for any number of events. Okay, but be careful, however, because a tree diagram can get messy. So an event is a group of outcomes within the sample space. So what's happening in those outcomes. So if we look on the second page, we are going to create a tree diagram. And you have the whole page to do this. Reason being because it can get messy and we have a lot going on here. So I'm going to start kind of in the middle of the page. All right, so we're going to say that this is player 1's player 1. So the first event is player 1. And what can player 1 or player A, I'll call it, what can player A throw out? Well, player A can be a rock, a paper, or a scissors. And each of those probabilities, if this person is totally random, has a 1/3 probability. We're going to assume they're all equally likely. The person just kind of randomly thinking it and doing it that way. So the events are kind of like in a column format, and the outcomes of that event are branches. So maybe we'll write that at the top. The events are columns of the tree. And the branches are the possible outcomes. Okay, so when a player A goes, they can throw a rock, paper, or scissors. Then player B would be the next event. So player B, again, can throw a rock, a paper, or a scissors. And again, we're going to assume 1/3 probability for everything. But now the fact that this gets messy is because now if player B threw a rock, then player B could also throw a rock, paper, scissors. But then we have to branch off rock, paper, scissors for all of these. So we have rock, paper, scissors, 1/3, 1/3, 1/3. And then also down here, rock, paper, scissors, 1/3, 1/3, and 1/3. Okay, so that was player B. Maybe I should move this over a little. All right, now the last, since there were 3 possible events going here, player A, B, and C, I have to draw a 3rd set of branches, a 3rd column for player C. Now player C is going to have a rock, paper, or scissors off of each of theirs. So we'll have, again, rock, paper, scissors, 1/3, 1/3, 1/3. Rock, paper, scissors. Rock, paper, scissors. And this is where it can get a little messy. So off of each of these, I need to do rock, paper, scissors. And even with me trying, it still got messy. So again, like we talked about, this is going to be one of the downfalls of the tree diagram, is that it is messy. So rock, paper, scissors. Sometimes you just have to extend the branches longer. And then down here, all right, so now that I have that tree diagram, here's what we need to know. That the total number of branches at the end is our total number of outcomes. So we can write this up here. Number of branches at the end is the total number of outcomes. And again, that's what we call the sample space. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. We have 27 total outcomes here. So if we look back here, where it says favorable outcomes over total outcomes for our theoretical probability, our total outcomes is always going to be 27 in this case, because there's 27 total branches at the end. So I'm going to do all my probabilities over here. So I need to find the probability of player A winning. So that's one probability of player A, probability of player B, and probability of player C. Now, the other thing you need to know for a tree diagram is that you multiply from branch to branch. Because that's what we call an AND probability. AND means to multiply in probability. Because, for example, if I want to know the probability of getting rock, 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 player A had to throw a rock, player B had to throw a rock, and player C all had to throw rocks. So I would multiply 1/3 times 1/3 times 1/3, which is 1/27. So in this case, all of these have a 1 out of 27 probability of occurring. But this isn't always the case. It just depends. All these had equal likely, but eventually we're getting the cases where the probabilities are different. Okay, so that'd be and so forth and so all the way down. So if we go look here now, probability player A again won when all three matched. So player A won with rock, rock, rock. So I'll put an A here. Player A would win with a paper, 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 which is right here. Again, that's 1 out of 27 as well. And player A would also win with a scissors, scissors, scissors. So that's player A. Again, that's 1 out of 27. So once you have that, then you add those. So I'd be adding for player A 1 out of 27 plus 1 out of 27 plus 1 out of 27, which is 3 over 27. Or 1/9. So player A has a probability of 1/9 chance of winning. We're going to do player C next. So player C wins when we do all three different. So player C would win if I did a rock, a paper, and then a scissors. So this would be player C. A rock, a scissors, and then a paper. So that would be player C. Again, 1 out of 27. A rock, a scissors, and then a paper. Oh, sorry. So we have 2 for rock. So then I can do paper, rock, scissors. So that would be B, 1 out of 27. A rock, a scissors, a paper. That would be B, 1 out of 27. And then I can do scissors, rock, paper. So that would be B. And then a scissors, paper, and rock. Again, 1 out of 27. So if we look here at our B's, we have, sorry, a C. These were C's. So we have a C here, a C here, and these are C's, sorry. A C here, a C here, here, and then a C here. So that's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 C's. So that's 1 out of 27 that we're adding 6 times. Which is going to be 6 over 27, or 2/9. So that has a little bit better of a probability. C has a little bit better probability of winning than A, which is what we kind of saw in our experimental results. Last, what I could do last is I could count all these other ones, which would be winning B, and that should get me the other way I could do it is I could know probability is always out of 1. In this case, 1 is 27 out of 27, and then subtract 1/9 and 2/9. And so this would be 9 out of a 9. And so we'd have a probability here of 6/9 or 2/3. So probability of B winning is 2/3, which is significantly higher. 6/9 compared to 1/9 and 2/9. That's why B won the most times. So again, this game is definitely not fair. If it was fair, they'd all have an equal probability of winning. So again, the other way I could do this, technically, is count all these other ones that don't have an A or C, which would be where B wins, and I would end up with 18 out of 27, which again reduces to 2/3. But again, it's probably a little bit easier knowing probabilities out of 1 and subtracting the rest. So that's our introduction to a tree diagram. A tree diagram is nice because you can do any number of events. So I could even do like 4 players, 5 players. But as we can see here, it does get messy.